Hello friends, welcome to the lecture of Applied Mathematics 2. Today we will discuss one more important topic. So let's start. In previous lecture, just recall that we have seen the first one, divergence of any vector, which is given by dot product of del with phi. Second one, we have seen that curl of any vector v is given by cross product of del with vector v. Also, we have seen that for curl of a vector v, it is said to be rotational or irrotational depending on condition. That is, any vector field is rotational if divergence of vector v any vector field is said to be rotational if curl of that vector v is non-zero, and the vector field is said to be irrotational, that is not rotating, if curl of vector v is 0. That is, we can easily identify that whether the vector field is rotating or not by just finding the curl of vector. It is also easy from here. If suppose we will consider curl as a rotation, and if rotation of vector v is 0, that is, it is not rotating. So this is the condition of irrotational. Also, one more important point, if curl of a vector is non-zero, then it is non-conservative, and if curl of a vector v equal to 0, then that field is conservative. So that is a very important point. Now, third most important point we will see in some example. To find scalar potential phi, we know that the gradient of scalar function is equal to vector, that we have seen in previous lecture. So by notation, gradient of scalar is denoted by del dot scalar function phi, which is equal to some vector, say vector f. So in order to find scalar potential phi, we will use this formula, that is vector f equal to del dot phi, in order to find scalar potential. Fourth important point, work done in moving an object from one point, say point A, to second point, say point B. So in order to find the work done, it depends on the field. That is, for conservative field and for non-conservative field, if we have to find work done, then for conservative field it is given by the formula integration d phi from point A to point B. But for non-conservative field, the work done is equal to integration with vector f dot dr over the curve. So these are the formulas that we will use in the example. So let us take first example. In this example, what is given? So given that vector A is given by x square plus xy square I plus y square plus x square y j, say equation number 1. And in first case we have to show that the field is irrotational. So first we will prove, first to prove given vector field A is irrotational, that is to prove curl of vector A is equal to 0. We know that by condition if curl of any vector is 0 then it is irrotational. So in order to prove we will first find curl of a vector A. So now curl of vector A is equal to, it is cross product of vector A with del. So it is equal to, now to find cross product we will use the determinant ijk. In next row we will write del by del x, del by del y and del by del z. Last row the components of vector A, which is given as x square plus xy square and y square plus x square y, but term of k is absent, so here it is 0. After simplification we will get I times 0 minus, now it is del by del z of y square plus x square y minus j times, now it is del by del x of this is 0 minus del by del z of x square plus xy square plus k times del by del x of y square plus x square y minus del by del y of x square plus xy square. In next step it is equal to, now I times 0 minus, now derivative of this with respect to z, it is constant because x and y are constant with respect to z, so it is 0 minus j times, again it is 0 minus derivative of this with respect to z, there is no z in this term, so derivative of this is 0 plus k times, now partially with respect to x, derivative of y square with respect to x, it is 0 plus derivative of x square, that is 2x into y, minus, now with respect to y, x square is constant, so it is 0 plus with respect to y, derivative of y square is 2y into x, so that is 2xy. After simplification it is I times 0 minus j times 0 plus k times 2xy minus 2xy, so it is 0, which is equal to 0. Therefore del cross vector A is equal to 0, that is curl of vector A is equal to 0, which means given vector field A is irrotational. In the same example we have to find scalar potential. To find scalar potential phi, we have gradient of scalar is equal to vector. Therefore by notation it is del with scalar phi is equal to vector which is given as vector A. Therefore, now we know that del is given by operator I del by del x plus j del by del y plus k del by del z dot with phi equal to given vector A. Therefore, it is equal to del phi by del x I plus del phi by del y j plus del phi by del z k, which is equal to given vector A, which is x square plus xy square I plus y square plus x square y j plus 0 k. Now on equating, we will get del phi by del x equal to x square plus xy square. That is, we have equated the coefficient of I. So we get del phi by del x equal to this. Similarly, equating coefficient of j, we will get del phi by del y equal to y square plus x square y, and del phi by del z, it is equal to 0. Say equation number 1, 2 and 3. Actually, in this example, we have to find the scalar potential phi. So, in order to get phi, we have to integrate this, so that derivative and integration will get cancelled and we will get the scalar potential function phi. So, integrating equation 1, 2 and 3 with respect to x, y and z respectively. So, equation 1 implies, now integrate equation 1 with respect to x. So, we will get phi equal to, with respect to x, integration of x square, that is x cube by 3 plus integration of x square by 2, and y square is constant plus some constant c1. Therefore, phi equal to x cube by 3 plus x square y square by 2 plus c1 is nothing but f of y comma z. Here observe that I have written f of yz in place of c1. Why? As we have integrated these with respect to x. So for x, y and z are constant. Again I am repeating, for x, y and z are constant. So we have replaced c1 by function of y and z. Now equation 2 implies, integrate equation 2 with respect to y. So integrate 2 with respect to y. We will get phi equal to, now it is y cube by 3 plus x square constant y square by 2 plus constant c2. So it is equal to y cube by 3 plus x square y square by 2 plus, now we have integrated equation 2 with respect to y, and for y, x and z are constant. So we will write c2 as f of x comma z. Also, equation 3 implies, now integrate equation 3 with respect to z, therefore phi equal to constant c3, integration of 0 is constant, which is equal to f of x comma y. Why we have taken C3 as f of x comma y? Because with respect to z, x and y are constant, so we have replaced C3 by f of x comma y. Say equation 4, equation 5 and equation 6. Now we will find f of yz, f of xz and f of xy. So for that we will follow the following process. So f of yz, it is equal to terms of phi independent of x, which is equal to f of yz is nothing but we have to, it is equal to terms of phi which does not contain x. So just observe in equation 4, 5 and equation 6, we have to find those terms which does not contain x. So in equation 4 here x is present, so we will skip this. Here again x is present. Now equation 5, here there is no x, so we will write it as y cube by 3. Next, here again x is present, so we will write f of yz as a y cube by 3. Now next, f of x comma z, it is terms of phi independent of y. So f of x comma z is nothing but those terms in equation 4, 5 and 6 which does not contain y. So it is equal to x cube by 3, because in this term y is absent. Now in this term y is present, so we will exclude this. Again here y is present, here is y present, so it is equal to x cube by 3. Similarly f of x comma y, so it is terms which not contain z, which is equal to, it is x cube by 3 plus y cube by 3 plus x square y square by 2. Now putting this constant f of yz or f of xz or f of xy in equation 4, 5, 6, we will get phi equal to x cube by 3 plus x square y square by 2 plus the value of fyz is y cube by 3. Also equation 5 implies, equation 5, phi equal to y cube by 3 plus x square y square by 2 plus f of xz, that is x cube by 3. Now look at these two equations, both are same. Therefore finally we get phi equal to, both are same, x cube by 3 plus x square y square by 2 plus y cube by 3 is a required scalar potential. This equation 7 is obtained by putting the constant f of yz in equation 4 and by putting constant f of xz in equation 5. So let's check whether the constant f of yz and f of x comma z is right or not. That is verification. For verification, differentiate the equation 7 partially with respect to x. We will get 7 implies del phi by del x, it is equal to 3x square divided by 3 plus derivative of x square, which is 2x y square as it is divided by 2 plus derivative of y cube by 3. With respect to x, it is 0, which is equal to x square plus xy square, that is del phi by del x. Now match this equation A with equation 1 that we have obtained in this example. For this, rewind and reverse back to equation 1. So from this we have seen that this equation A and equation 1 are same, and that's why the constant that we have find is right. Similarly, you can find del phi by del y and del phi by del z in order to check whether the constants are correct or not. That is our verification. So this is simple example 1 based on divergence and curl.